From towering bridges to underground tunnels, every construction project begins with a bold vision and transforms into a feat of engineering brilliance. Trailer Home manufactures the Goldhofer THPSL model, self-propelled modular trailer for transporting extremely heavy loads. Designed with a hydrostatic drive system, it delivers smooth, jolt-free movement with infinitely variable speed control, even under tough conditions. Its tractive power depends on the number of driven axle lines and the engine capacity of the power pack. These trailers are widely used in the offshore sector, power plants, and industrial plant engineering. In addition to transportation, the SPMT plays a vital role in precisely positioning large and heavy components. Trailer Home's modular design ensures flexibility and efficiency in handling the most demanding logistical challenges across various industries. The Dafaku Bridge is a remarkable concrete-filled steel tube arch bridge located in Zunyi, Guizhou Province, China. Spanning 1,427 meters with a main span of 410 meters, it soars to a height of 280 meters above the valley floor. This impressive structure is a key component of the Renhuai-Zunyi Expressway, supporting 6 traffic lanes in each direction and greatly improving connectivity in the region. Noted for its modern engineering and bold design, the bridge features a striking red arch that contrasts beautifully with the natural landscape. As one of the many extraordinary bridges in Guizhou, the Dafaku Bridge stands out as a symbol of China's advancements in large-scale infrastructure and aesthetic bridge construction. The capital Diamond Tower is a 52-story twisted skyscraper under construction in Egypt's new administrative capital. Developed by Amazon Developments, it is the tallest twisted tower in Africa and the first of its kind on the continent. Located in the central business district along the North Bin Zayed axis, the tower features a striking 180-degree twist, offering stunning panoramic views. It houses commercial units on the lower floors, administrative offices in the middle, hotel suites above, and a revolving restaurant at the top. With a diamond-shaped crown and 360-degree views, the tower also includes a health club and has become a landmark project in Egypt's growing skyline. The Eurasia Tunnel, officially known as the Istanbul-Bosphorus Road Tube Crossing Project, is a groundbreaking infrastructure development that connects the European and Asian sides of Istanbul beneath the Bosphorus Strait. Construction began on February 26, 2011, and the tunnel opened to traffic in December 2016. Ahead of the contractual target of August 2017. This 5.4 kilometers two-level tunnel, reaching a depth of 106 meters below sea level, was built using advanced tunnel boring machine technology. It links Kennedy Street in Kumkapi, Europe, to the D100 highway in Kosiolu, Asia, aiming to ease traffic congestion and reduce travel times. The project included a total of 9.2 kilometers of road improvements on both continents and was completed in 55 months. Operated by Atos under a 24-year, 5-month concession, the tunnel will be handed over to the state in 2043. It initially offered a traffic guarantee of 68,500 vehicles per day, which has since increased to over 82,000 daily, peaking at 94,459 in 2024. The tunnel accommodates two-way traffic in a safe, weather-resistant environment and, since 2022, has allowed over 2 million motorcycles to pass through. It is Istanbul's second undersea tunnel after Marmaray. The construction of the Sabetta multifunctional marine port on the Yamal Peninsula stands as a monumental hydraulic engineering achievement in the Russian Arctic. This strategically vital project was carried out between 2012 and 2017 under extreme environmental conditions and included both preparatory and main construction phases, with extensive work on coastal and offshore infrastructure. During the preparatory phase, 4 berths with a total length of 975 meters were constructed, requiring approximately 15,000 tons of steel and 500,000 tons of inert materials. Additionally, the initial elements of the southeastern ice protection facility were built within the artificial land zone, alongside the base for a vital technological trestle. These works involved 26,800 tons of steel, 27,000 cubic meters of concrete, and 330,000 tons of inert materials. The main construction phase expanded upon this foundation with the creation of the Deepwater section of the southeastern ice protection facility and the massive northwestern ice protection structure. These elements required an additional 44,000 tons of steel, 73,000 cubic meters of concrete, and 200,000 tons of inert materials to ensure durability against the harsh Arctic ice conditions. A critical component of the project included 2 high-capacity technological berths for loading LNG and gas condensate. Each berth featured 2 mooring/docking dolphins and 6 mooring dolphins, demanding 19,700 tons of steel, 31,000 cubic meters of concrete, and 75,000 tons of inert materials. Each berth Pile driving formed a central part of the entire project. From 2012 to 2016, over 80,000 tons of piles were driven into the seabed. By the end of the project in 2017, more than 110,000 tons of piles, some reaching lengths of up to 50 meters, had been successfully installed, ensuring the long-term stability of all marine structures. This comprehensive hydraulic construction project reflects the capabilities of MRTS and its partners in delivering large-scale marine infrastructure in one of the world's most demanding environments, enabling year-round maritime access and supporting Russia's energy exports from the Arctic. The Port Mann water supply tunnel, located southeast of downtown Vancouver, is a vital part of Metro Vancouver's regional water network. Overcoming extreme tunneling pressures and complex geological conditions, it showcases Canadian innovation in high-pressure, soft-ground tunneling. It earned TAC's 2016 Canadian Innovation Project of the Year. Arsenault Wilson & Cole completed the longest direct pipe installation in North America and only the 4th of its kind in the United States. This 3,052-foot project involved installing a 48-inch diameter steel pipeline beneath critical infrastructure to connect the municipal water plant in Port Arthur, Texas, to the LNG facility in Cameron Parish, Louisiana, 17 miles away. The alignment passed under a U.S. Army Corps of Engineers hurricane protection levee, a railroad switchyard storing up to 500 rail cars, and the 1,000-foot-wide Sabine-Neches Canal, one of the nation's busiest waterways. Because the native soil, consisting of firm to silty clay, could not safely support high-pressure drilling, traditional horizontal directional drilling was ruled out. Instead, the team employed the direct pipe method, which combines microtunneling with a 750 metric ton hydraulic thruster. The pipe was laid out behind the launch pit and advanced forward as excavation occurred, reducing hydraulic fracture risk. A bentonite slurry carried excavated soil back through the pipe to a separation plant for recycling. Despite a narrow 120-foot wide construction corridor between a residential area and State Highway 82, AWC overcame space limitations through careful planning. Only 2,100 feet were available for the pipeline layout, requiring an additional 1,400 feet to be welded and inserted during drilling. Highway access was rerouted, and a 15-foot-tall, 900-foot-long sound wall was erected to minimize disturbance to nearby residents. Driveway and carport modifications were also made to maintain access. After 29 days of 24/7 drilling, the pipeline broke through with pinpoint accuracy into a public park. A 30-inch HDPE carrier pipe was later pulled through the steel casing. Full site restoration followed within 21 days. The entire project, from approval to completion, was finished in under 5 months, well ahead of schedule, showcasing AWC's innovation, precision, and engineering expertise in one of the most challenging trenchless pipeline projects ever executed in North America. A Goldhofer self-propelled modular transporter, SPMT, is used to transport a large and heavy industrial component. The process begins with precise alignment of multiple modular units to form a platform capable of supporting the massive load. Each module is self-propelled and equipped with hydraulic suspension and multi-directional steering, allowing for coordinated and stable movement. The component is carefully loaded onto the SPMT using hydraulic lifting mechanisms, which raise the cargo off the ground without the need for cranes. Once secured, the transport operation starts at a controlled speed, with multiple operators supervising the movement through remote control systems. The vehicle maneuvers through narrow paths and curves with impressive precision thanks to its individually steerable axle lines. Throughout the journey, the load is kept level and stable by continuously adjusting the hydraulic suspension. The SPMT moves over uneven surfaces and slight inclines without causing vibrations or destabilizing the cargo. In tight areas, the SPMT performs crab steering and even rotates in place to navigate through challenging zones. At the destination, the transporter performs fine positioning to align the component with its final location. Hydraulic systems lower the load gradually and precisely onto its supports. The entire process is executed without external towing equipment, relying entirely on the self-propelled capabilities of the SPMT modules. This method ensures safe, efficient, and precise handling of extremely heavy cargo, minimizing risk and eliminating the need for complex rigging or lifting operations. Hidden deep beneath the River Thames, the Thames Tideway Tunnel is a colossal engineering project aimed at cleaning up London's iconic river,
A labyrinth of interconnecting tunnels that one day will clean up.
stretching 16 miles and reaching depths of 40 meters. This new super sewer will intercept overflow from the city's most polluting sewers, preventing waste from entering the Thames during heavy rainfall.
What it does is it links up all the most polluting sewers.
The tunnel links areas from Acton to East London and features intricate connecting chambers lined with spray concrete.
Sewage will all come into here.
Once completed in 2025, it will dramatically reduce sewage discharges, protect the river's ecosystem, and improve water quality, benefiting both the environment and millions of Londoners for generations to come. Construction of SoFi Stadium began in November 2016 in Inglewood, California. To meet FAA flight path requirements, crews excavated 100 feet below grade, removing 7 million cubic yards of earth. Nearly 100,000 tons of steel and 144,000 cubic yards of concrete were used. The stadium features a 1.2 million square foot translucent ETFE roof with 20 million ventilation holes and the world's largest center-hung scoreboard, the Samsung Infinity Screen. Designed for seismic safety, the seating bowl includes special dampers. Over 17,000 workers contributed, with up to 3,500 on-site daily. Despite heavy rains in 2017 and the COVID-19 pandemic, the stadium opened on September 8, 2020. Located 135 miles off the Louisiana coast, the Insco DS-5 is an ultra-deepwater drill ship operating in over 8,100 feet of water, drilling to depths near 27,500 feet. This 24/7 operation uses advanced drilling technology and is staffed by a professional, well-trained crew. Workers arrive by helicopter and follow a 12 hours on, 12 hours off schedule for 21 days, followed by 21 days off, working only half the year for a full year's salary. Each shift starts with a safety meeting. Safety is paramount and reinforced by training coordinators. The rig operates like a floating village, requiring various specialists, marine crew, drillers, maintenance, medical staff, and catering workers. The offshore installation manager oversees drilling, while the master commands the vessel. The DS-5 features a 200-foot-tall derrick capable of lifting 2 million pounds of riser pipe. Drilling and pipe handling are largely automated. Below the deck is a moon pool for deploying drill pipes, and ROVs inspect equipment underwater. The ship's dynamic positioning system uses 6 thrusters and GPS to maintain position above the well. With a maximum capacity of 200 people, strong camaraderie develops among multinational crew members. Facilities include a gym and dining area, making life on board both challenging and rewarding, like having a second family at sea. Based on the August 2016 4K construction update of Apple Campus 2, remarkable progress was being made across the expansive site. The central structure, famously referred to as the spaceship, was rapidly taking shape, with cranes actively lifting iron beams into position to complete the circular framework. Considerable advancements were seen on the roof, where HVAC systems were being installed and preparations for solar panels were underway. Frames for the solar arrays were staged and ready to be lifted into place, signaling Apple's strong commitment to renewable energy. Inside the ring, plans were in place to create a landscaped garden and pond, adding natural beauty and promoting wellness among employees. The foam-lined tunnels and underground parking garage systems were being covered with dirt as the landscaping process had already begun. A once massive mountain of dirt on site was steadily shrinking as the soil was redistributed. The 100,000 square foot corporate fitness center was under construction, offering facilities for physical wellness. In front of the main building, basketball and tennis courts were planned, further emphasizing Apple's investment in employee health and recreation. Around the main campus, construction of multiple smaller research and development facilities was underway, supporting the central R&D hub. Nearby buildings were being adapted for office and R&D purposes as well. To the North Tontao Auditorium and an adjoining V. Work had also begun on a 2,500 square foot maintenance facility to support ongoing operations. The parking structures, encompassing an enormous 2 million square feet, were a key component of the campus infrastructure. Alongside these garages, fuel cells and backup generators were being installed to ensure a reliable and sustainable energy supply. The security kiosk was taking shape at the main entrance, highlighting the importance of access control on the high-profile campus. The site remained busy, with numerous cranes hard at work across all sections. Overall, the Apple Campus 2 project reflected not only architectural innovation, but also environmental responsibility and employee-centered design. The combination of green energy, high-tech research spaces, recreational facilities, and landscaped environments showcased Apple's ambitious vision for the future workplace. Apple Campus 2, known as the Spaceship, is a ring-shaped headquarters with a 1,512-foot diameter and 4,805-foot circumference. Designed with extreme precision, it includes 4 above-ground floors and 3 underground levels. The main circular building houses most employees, with interior and exterior walls made entirely of glass. Roads and parking are placed underground, preserving the natural surroundings. The central courtyard features a 30-acre park with orchards, paths, and a pond. The structure includes 4,300 hollow concrete slabs that serve as both floor and HVAC system. Apple partnered with firms from 19 countries, using specially selected maple wood and oversized glass panes. The construction generated 13,000 full-time jobs and was marked by Apple's signature attention to detail, even requiring workers to wear gloves. The Russky Bridge, spanning the eastern Bosphorus Strait in Vladivostok, Russia, is an engineering marvel and the longest cable-stayed bridge in the world. Its central span measures 1,104 meters, 3,622 feet, making it a global record holder. The bridge connects Russky Island to the mainland and was built to support the 2012 APEC summit hosted on the island. In addition to its record-breaking main span, it features the second tallest pylons in the world, standing at 324 meters, 1,063 feet, and has the longest cable stays ever installed on a bridge. The construction site presented numerous challenges. The strait is 1,460 meters, 4,790 feet, wide and navigable to depths of up to 50 meters, 160 feet. The local climate is harsh and unpredictable, with temperatures ranging from -31 to +37 degrees Celsius, strong storms with wind speeds up to 36 meters per second, 130 kilometers per hour or 81 miles per hour, wave heights reaching 6 meters, 20 feet, and winter ice up to 70 centimeters, 28 inches, thick. These conditions required innovative engineering solutions and durable materials. Construction of the bridge pylons began in September 2009. On Russky Island, deep foundations were laid using 120 auger piles per tower, each drilled to a depth of 77 meters, 253 feet. The pylons were built using specially designed self-climbing formwork, allowing for efficient and high-quality concrete pours of 4.5 meters, 15 feet at a time. Initially, cranes helped position the first 3 pours, but the formwork system was later moved independently. Due to the pylon's A-shaped geometry, standardized forms were unusable. Each tower required a unique set of custom-designed forms. Transitioning between structural sections occurred at heights of 66.26 meters, 217.4 feet, and 191.48 meters, 628.2 feet. Above 197.5 meters, 648 feet, work began on the anchorage zones for the cable stays. The bridge towers were constructed in parallel with the installation of cable stays, which significantly reduced the construction timeline. The central span of the bridge features an aerodynamic cross-section, precisely shaped through computational modeling and wind tunnel testing. This design helps the bridge withstand sudden gusts and constant wind loads common in the region. The orthotropic deck includes longitudinal and transverse joints which were welded on site. These joints connect vertical walls, ribs, beams, and diaphragms, and are reinforced using high-strength bolts. Large, prefabricated sections of the central span were fabricated off-site and transported to the installation area via barge. Once at the site, these segments were hoisted to a height of 76 meters, 249 feet, aligned precisely and connected. Afterward, the cable stays were anchored to support the segments in place. The cable-stayed system plays a critical role in bearing all static and dynamic loads of the bridge. Rather than being permanent components, the cable stays are designed to be serviceable and replaceable. They are engineered to endure harsh weather and environmental conditions. Each cable stay consists of 13 to 79 parallel strands, each 15.7 millimeters, 0.62 inches in diameter and made of galvanized steel wires. The shortest cable stay measures 135.771 meters, 445.44 feet, while the longest reaches 579.83 meters, 1,902.3 feet. To protect them from the elements, the stays are encased in high-density polyethylene sheaths, which are resistant to ultraviolet light and temperature extremes from -40 to +40 degrees Celsius. The bridge has a total length of 1,885.53 meters, 6,186.1 feet, with an overall footprint, including trestles, extending 3,100 meters, 10,200 feet. The deck is 29.5 meters, 97 feet wide, with a 23.8 meter, 8 feet wide roadway supporting 4 traffic lanes, 2 in each direction. The bridge offers a clearance of 70 meters 230 feet beneath the central span, allowing large ships to pass freely. In total, 168 cable stays support the structure, fixed to 2 towering pylons. In summary, the Russky Island Bridge stands as a feat of modern engineering. It blends record-breaking dimensions, intelligent design, and robust materials to overcome extreme environmental challenges and deliver a vital connection to Russky Island. Its completion not only demonstrated Russia's engineering capabilities, but also contributed to regional development and international cooperation.